Back again. So this is going to be part number 6 of Virtual Topologies in MPI and episode number 34 of Learning by Doing MPI. We're going to continue from where we left off last time. I actually forgot to mention this last thing about MPI cart shift. It is erroneous to call MPI cart shift with a direction that is either negative or greater than or equal to the number of dimensions in a Cartesian communicator. So basically, you understood that this MPI cart shift is to calculate your neighboring processes, which is going to be source, destination, one to the left, one to the right, or if it's in the first direction, which is going to be row, columns, and this is the first direction. Then it's going to be up and down, it's going to be left, right, up, down, and then the back and front in a three-dimensional Cartesian structure or Cartesian grid. Then the next thing on the line was partitioning of Cartesian structures, which you can use MPI cart sub. Do I have an example for this? It seems like, let me see, Vim MPI cart sub. I do, I forgot to mention this, so I'm gonna add that. C MPI cart sub.c. Forgot to add it here. Okay, so what you're gonna pass in is your communicator, and then remaining dimensions that you want, you're gonna pass in. That's an input, and then you're gonna get your new communicator. And what it does, this is sort of a logical array, depending on the dimensions that you have. And then what you do with that array is that you say, hey, true, false, true, or if it's a three-dimensional structure. If it's a two-dimensional, you can say like true, false, false, true, or whatever. But this is how you can create sub-Cartesian structures or sub-Cartesian grids from mother Cartesian grids. Okay. And you can read these stuff yourself. I think it's quite straightforward. Oh, I mentioned it here, MPI cart sub. Okay, before. Yeah, anyways. So we have an example 8.8. It's a scenario that we have a three-dimensional grid. It's 2 by 3 by 4. And what we want to do is to use a remain dimensions or remain dims of true, false, and true. That's the pattern we want to have. So this is a 2 by 3 by 4 grid, and then we don't have any periodicity, and the coordinates is also going to have 3, and then we print some information as before, and we create it, and then, do the coordination, and then coordinates, and then print stuff with the coordinate information you get for every rank, and then use the barrier to make sure that things are printed in order. And then what you want to do is to create a new sub-cart communicator that is a new sub-Cartesian communicator, and then we're going to say true, false, true. This is exactly the same pattern here, true, false, true. Then doing that, since the middle one is false, then this means that this is going to be gone with the wind, and what is left is 2 by 4. So you're gonna end up by having 3 communicators, which they have a 2 by 4 grid. So that is what's going to happen. This is also what it says here. We'll create 3 communicators, each with 8 MPI processes in a 2 by 4 sort of Cartesian topology. So this is what we try to do here, and then we use those inquiry functions to find the new dimensions, to find, we use this cartdim get to get the new dimensions, print the number of dimensions, and then use that MPI cart get to get extra information about that, the list of those processes, the periodicity information, and the coordinates. And so this is the same drill as we have seen in previous examples for Cartesian grids. But in this case, in the freeing part, also make sure that you're freeing both Cartesian communicator and the new sub-cart communicator. So if I say MPI CC MPI cart sub, and we run it, we got to use 24 processes. The reason we got to use 24 processes is that our initial grid is 2 times 3 times 4. So 6 times 4 is 24. That's why we need 24. And then we print all that information. And then what is important is that new sub-cart the new Cartesian communicator that we have created from the original or the mother Cartesian communicator has 2 dimensions, and those dimensions or the grid is 2 by 4. And as we said, like we're going to have 3 communicators with 2 by 4 8 processes in every sort of Cartesian, every sub-Cartesian communicator. And then you see that information about the periodicity is 0 and 0. Of course, because we were not using periodic conditions. And then you know that root proc has the following coordinates in the subcard com. You see that root proc now has only 2 values because it's a 2-dimensional subcommunicator or a sub-Cartesian communicator. So that's the difference. And the original sort of values for coordinates that it had, the root process had 0, 0, and 0. Okay, so now moving to the last sort of couple of, or the last 2, I think, lower-level topology functions or inquiry functions. In this case, it's MPI cart map and MPI graph map, which is the next one after this. And usually these functions, as a user, you don't need to call them. Let me read this. The 2 additional functions introduced in this section can be used to implement all other topology functions. In general, they will not be called by the user directly, except when creating additional virtual topology capabilities other than those provided by the MPI standard. The 2 calls are both local. These calls are also local. MPI cart map, you're going to pass in your communicator, number of dimensions, and dimensions array, which is basically number of processes in every direction. Then periodic conditions or periodic array, and then it's going to give you basically your new rank. Reordered rank of the calling MPI process, MPI undefined if the MPI process is not part of that basically grid. Okay. We do have an example for this MPI cart map. So with MPI cart map. But before diving into that, let's see the rest of it. It says MPI cart map computes an optimal placement for the calling MPI process on the physical machine. A possible implementation of this function is to always return the rank of the calling MPI process, that is not to perform any reordering at all. And this is an advice to implementers. If you want, you can read it, but you can see, for example, like this is a very beautiful example of the function MPI cart create. This is for creation of Cartesian topologies. Then it says that you could maybe implement this by, with the reorder of true can be implemented by calling MPI cart map with that, and then calling MPI com split, and then with the color of 0, you know? So you can use combination of this cart map, graph map, and stuff like that in conjunction with MPI com split, and then you can try to mimic the implementation of MPI cart create. So as we said, these 2, as a user, you don't need to basically use them directly in your code, and the example is also quite simple. Like these things we use every time, but this is like a dummy example just to show you how the syntax works. One thing which is important is that you cannot pass in a already Cartesian communicator, or if you're using MPI graph map, you cannot use an already graph sort of virtual topology or communicator which has those information associated with that. So it has to be something like MPI com world. And then here in this case we had 3 by 3, it's going to be 9 processes, and notice that we are using 12 processes, so 3 processes are going to be basically out of that, and we don't have any periodicity, and every basically process, if they don't have MPI undefined, because for 3 of those processes, because 3 by 3 is a 9, 12 minus 9 is going to be 3, so 3 processes are going to have, for the new rank, they're going to have MPI undefined. So this is part of what happens in MPI cart map. If you're not part of that, we said MPI undefined is going to get returned if you're not belong to the Cartesian grid. There is a corresponding, let's usually say that's a cousin of that. Again, the standard here sort of when they want to talk about the map, they start with Cartesian first and then they go to graph. But in the beginning of inquiry functions, they started with graphs first and then they went to Cartesian sort of grids. Anyways, it also works the same way more or less. We have a I haven't run this one, MPI CC. MPI cart map. And let's run it with, oops, it should be 12 processes. Now you see that proc 0 is mapped to 0. Of course, there's no reordering happening here. You see 4 to 4, 8 to 8, 1 to 1. And then you see that the maximum sort of index we have is process 8, which is 0 to 8 is going to be 9 processes, and 3 of them, they're going to have MPI undefined. And the same example is with graph map. Exactly the same scenario. Here we have this 2, 3, 4, 6. Is it an example in the... No, there's no example here, but we have in this case 2, 3, 4, 6, and this is the pattern. Oh, this is the first example we have for graphs. We had 1, 3 for process 0. We had 1 and 3 as the neighbors, and then process 1 had 0 as a neighbor. Process 2 had 3 as the neighbor, and process 3 had processes 0 and 2 as neighbors. And then here we pass in to MPI graph map the MPI world. Again, you cannot use a graph sort of topology as a communicator here. It has to be something like MPI world. You pass in the size, the index, and the edges. And yeah, and then you ask for the reordered rank or the what is going to be the mapped ranked. And then we say process rank is going to be mapped to this rank. So again, MPI CC, MPI graph map, and we run it with, of course, 4 processes. In this case, you see that 0 to 0 is mapped, 2 to 2, and 1 to 1. You see that there is no reordering happening here or no remapping happening here. Okay, we're done with inquiry functions. Now we're going to continue with neighborhood collective communications on virtual topologies. So virtual topologies specify a communication graph, but they implement no communication functions themselves. Many applications require a sparse nearest neighbor communication that can be expressed as graph topologies. Okay. We describe several collective operations that perform communication along the edges of a graph representing a virtual topology. All of these functions are collective. This is super important. You already know what that means. If you don't know, then please go back to the chapter number 6, I think, in the MPI standard, which was about collective communications. They must be called by all MPI processes and the specified communicator. In a nutshell, that's what it means. And see section 6, that's the chapter I was talking about, for an overview of other dense or global collective communication operations and the semantics of collective operations. It is sort of nice that it uses sort of the vocabulary of dense collective communication operations or global collective communication operations. The reason for that is in graphs, you don't have like all the connections or, you know, all those like neural networks connected to either. Everything is connected to each other. No. In this case, depending on the structure you have, the problem you have, or sort of the let's say the geometry or the structure of your problem, you're going to have a different sort of graph, or you're going to have a different Cartesian grid. So yeah, if the graph was created with MPI disk graph created adjacent with sources and destinations containing 0 to the n-1 with n number of the MPI processes in the group of com-old, the graph is fully connected and also includes an edge from each node to itself. Then the sparse neighborhood communication routine, which is what we want to talk about right now, performs the same data exchange as the corresponding dense or fully connected or those global collective operations in chapter 6. So this is a far extent or extreme of the case of this sparse neighborhood communication operations, which if everything is interconnected, then they're going to represent the same operations as those fully connected dense or global collective communication operations. In the case of a Cartesian communicator, the only nearest neighbor communication is provided, corresponding rank source and rank dest when you're using this MPI cart shift with displacement of 1. So if you have a molecule in a 3-dimensional Cartesian grid, so you have how many neighbors? You have 6 neighbors. You have your left and right, you have your up and down, and you have your front and back. So this is quite similar also to what you do, for example, in CFD, you know? When you have a 3-dimensional geometry, you have a computational cell, then you have your neighboring computational cells by up, down, left, right, you know, or usually they showed it by north, east, like west, something like that, south, and stuff like that. Anyways, we have a rationale here. Neighborhood collective communications enable communication on a virtual topology. This high-level specification of data exchange among neighboring MPI processes enable optimization in the MPI library because the communication pattern is known statically with the topology information that we fit in. Thus, the implementation can compute optimized message schedules during creation of the topology. If you are interested, you can see the reference number 40. This functionality can significantly simplify the implementation of neighbor exchanges. Reference 36 for more information. That was just a rationale. So for a distributed graph topology created with MPI disk graph create, the sequence of neighbors in the send and receive buffers at each MPI process is defined as the sequence returned by MPI disk graph neighbors for destinations and sources respectively. For a general graph topology created with MPI graph create, the use of neighborhood collective communication is restricted to adjacency matrices, where the number of edges between any two MPI processes is defined to be the same for both MPI processes with a symmetric adjacency matrix. In this case, the order of neighbors in the send and receive buffers is defined as the sequence of neighbors as returned by MPI graph neighbors. And note that graph topologies should generally be replaced by distributed graph topologies because distributed graph topologies are scalable. They have better efficiency and performance when you're working with huge problems. For Cartesian topology, on the other hand, created with MPI cart create, the sequence of neighbors in the send and receive buffers at each MPI process is defined by the order of the dimensions. First, the neighbor in the negative direction. So if you are in the row major, so it's going to be previous raw and then the next raw, and then in the positive direction. If you're in the column direction, then it's going to be the column to the left first and then the column to the right. So that's negative first and then positive. The numbers of sources and destinations in the communication routines are 2 times n dimensions, with n dims defined by MPI cart create. That's communication routines, the number of sources and destinations in that communication routines. For example, if you have a 2x2 grid, can I draw something here? Like if you have a 2x2 grid, something like this, and this, and this, then you're going to have these, and these, and then this, and this. So you see that it's going to be 4, and that is 2 times n dims, number of dimensions. We have 2 dimensions, 2 times 2 is 4, and that is we have 2 sort of sources and destinations for communication routines. Okay, if a neighbor doesn't exist at a border of a Cartesian topology, in the case of non-periodic virtual grid dimension, if the periods are false, then this neighbor is defined to be MPI proc null. So this is also very, very important. Similar to what we had also before, that we have seen this behavior. If you have periodic condition, then it's going to consider that. I think we have seen it in MPI cart shift, when we want to calculate the shift, like, you know, the negative direction, the positive direction neighbors. And then we saw that if we don't have any, it's going to return -1. And if we have periodic condition, it's going to return basically the maximum value, or the one which is at the end of that array. If a neighbor in any of the functions MPI proc null, then the neighbor collective communication behaves like a point-to-point communication with MPI proc null in this direction. So it's like a dummy. And you remember in point-to-point communication. If you don't remember, please go back to, I think it was the first series in chapter 3, point-to-point communications in MPI. That we have seen the effect of this MPI proc null, and I do remember that I stressed that this MPI proc null is super, super important in cases when you are having, you know, boundaries or, you know, things which are out of bound. You can use it as a dummy sort of let's say send or receive source sort of. Okay, that is, the buffers is still part of the sequence of neighbors, but it is neither communicated nor updated. So the first one is neighborhood gather. If, whoops, let me take that out. In the neighborhood gather operation, each MPI process I gathers data, so it receives data, in other words, from each MPI process J if an edge of J and I exists in the topology graph, sorry. So J is the sender and I is the receiver. And each MPI process I sends the same data items to all MPI processes j where an edge of I and j exists. So again, I is the sender this time and j is the receiver. The send buffer is sent to each neighboring MPI process, and the else block in the receive buffer is received from the else neighbor. That's also super important. And here we do have like 3 variations of examples to basically give you a whole picture of MPI neighbor all gather. Let's first see what things do we need here. We need send buffer, send count, send type. We have seen this pattern billions of times in those point-to-point communications, collective communications, you know. And then receive buffer, receive count, receive types. You already know everything, what it means. And then you got to pass in your communicator. And that communicator is going to be a communicator with some associated ritual topology, because this neighbor all gather works on ritual topologies. Either it's going to be Cartesian grid or it's going to be graphs, or distributed graphs for that matter. And everything is an input parameter, but the only output is going to be the receive buffer. And the meaning of everything here is quite straightforward. I don't want to spend time on it. Let's see if you have extra information here. It says that MPI neighbor altogether also supports everything: Cartesian communicators, graph communicators, and distributed graph communicators. And if com is a distributed graph communicator, the outcome is as if each MPI process executes sends to outgoing neighbors that it has, or receives from the, let's say, its incoming neighbors. It executes also receive operations. So this is also how, basically, this is exactly this sentence right there. It translated into sort of some code. But we don't care about that right now. And then we have with a figure also, you know, a picture basically says 1,000 words. So you have also a picture here, for example, for a node here. You see that these S with indices 0, 1, and 2, those are the sources basically. And sources in those graphs, it means that other MPI processes are going to send to that current MPI process. And these D with sub of 0, 1, 2, 3, 4, 5. Sorry, the S indices were from 0 all the way up to 5. And the D indices, they start from 0 to all the way up to 3. That's the maximum you have. So that is why you have a receive buffer of 5, or actually 6. The index is 5, but you start from 0, so you have 6 values to be received. And the reason for that is because the current process needs to receive information from these sources. And destination is basically, it uses the same send buffer to send data to, for example, neighbor number 0, neighbor number 1, neighbor number 2, and neighbor number 3. And you see that the direction of the array shows that whether this MPI process is going to send information or whether it's going to receive information. You see that, for example, for S0, the direction is towards the MPI process, and for this one, it's outgoing from the process. That's the picture. If you want a nicer graphics, this one shows a Cartesian neighborhood all-gather example with, if you have a Cartesian with one dimension, it looks like this. So it sends and appends it to that array, and then it receives also from the other one. So in this case, you're going to have your receive buffer with size of 2. So it sends, receives, sends, receives. In this case, you're going to have a periodic condition. So if it goes to the left neighbor, it's going to be itself. If it's going to right neighbor, then it's going to be again itself. So that is why we have the blue arrow and these sort of dashed lines, both of them sort of originating from the same process. But if you have 3 processes in one dimension, like the one on the left, you see that, for example, for this one, whoops. So I'm going to finish this, and then we're going to continue in the next episode. So you see that for this one, for example, when you have 3 processes in one dimension, then you see this one sends with the periodic condition. It sends to the last neighbor, because to the left it has no neighbor, to the left it has no neighbor. So that is why it sends it all the way with periodic conditions to the right side of this receive buffer. And then the left side is going to be filled with the middle process. It's going to put the 200 information there. What is happening with the middle one is that it's going to be filled, the right side of the receive buffer is going to get filled with this process, the one on the right, and this one is going to get filled with the one on the left. So that is why you have 100 and 300. And then for 400 itself, it's going to receive from its right, which is 200. It's going to receive it to the right. And then from the left, when it wants to receive, it has no neighbor, but it basically receives it because since we have periodic conditions. So this is with periodicity, I just put it here to stress that what is happening right there. And now we can probably take a look at the example, and then I'm going to finish this episode. It was, oh no, actually we have 3 examples here. So I'm going to skip this totally, and then we're going to see the actual code in the next example. In the next episode, sorry.